We are jumping right in today with a paper that could really change the game for image generation. It's called DeCo, Frequency-Decoupled Pixel Diffusion for End-to-End Image Generation.
Yeah, and this one is worth a deep look because it tackles what has been the biggest bottleneck for pure pixel diffusion models.
Right. If you ever worked with something like a DIT, a diffusion transformer, you know the main issue is that they are just incredibly slow.
Painfully slow. And it's because you're forcing this single massive model to do two completely different jobs at the same time. You've got the complex high-frequency stuff like noise, texture.
All the tiny detail.
Exactly. And then you have the low-frequency semantics, the actual structure of the image, the shapes, the layout. The model gets bogged down trying to learn both.
So it's just distracted. And DeCo's solution is, well, it's architectural.
Totally. They've introduced what they call a frequency-decoupled framework, so they separate the work. The big diffusion transformer, the DIT, now only has to focus on the low-frequency semantics, and it does that using a much easier downsampled input.
And it offloads the hard part.
It offloads all the tricky high-res detail generation to a separate, really lightweight, and importantly, attention-free pixel decoder. And that decoder is conditioned on what the DIT figures out.
And the results are pretty staggering. I mean, not only is it state-of-the-art for pixel models, hitting an FIB of 1.62 on ImageNet,
which puts it right up there with the best VAE-based models.
But the speed is the real story. It can reach competitive quality up to 10 times faster in terms of training iterations. That's the core finding we need to unpack for you today.
Yeah, it's a huge deal.
So let's start by setting the scene a little. For a while now, the generative world has been split. You had latent diffusion on one side, pixel diffusion on the other.
Right, and latent diffusion, models like stable diffusion, they really won the first round.
And why was that? Why did they take over so quickly?
It was all about practicality. When you use a variational autoencoder, a VAE, you're basically squishing this massive high-dimensional image down into a much smaller, more manageable latent space.
You're simplifying the problem.
Massively. The diffusion process becomes so much cheaper and easier to handle computationally. You're trading, perfect pixel modeling for just being able to train the model in the first place.
Okay, so it's a smart computational shortcut. But there's always a catch with shortcuts, right? What's the cost?
The cost is the VAE itself. That's your bottleneck.
Yeah.
It doesn't matter how incredible your diffusion model is. Your final image quality can never be better than the VAE's ability to reconstruct the image from that compressed space.
And that's where you get those weird little artifacts sometimes, a bit of blurriness or strange textures.
Exactly. Those are often VAE artifacts creeping in. And on top of that, just training the VAE is its own separate, complicated problem. You often need adversarial losses, extra supervision. It just adds a whole other layer of complexity.
Which is what pixel diffusion was supposed to solve. Just model the raw pixels directly, no middleman, no VAE bottleneck. You get, in theory, perfect distribution learning.
In theory, yes. But then you run headfirst into that other massive barrier, the sheer computational nightmare of it all.
Because you're asking one model to do too much.
Precisely. You take a standard DIT and throw it at raw pixel space, and you're asking it to learn two completely different kinds of signals.
Yeah.
You have the low-frequency stuff, the overall structure, where the cat is, the shape of the building. That's, relatively easy to learn.
But the high-frequency signals, that's the part that kills performance.
It's devastatingly complex. We're talking about random noise, fine textures, the subtle little flickers of light. It's like high-dimensional static. And a general-purpose model like a DIT spends a huge amount of its energy trying to perfectly map every single one of those random pixel values.
It's optimizing for things we can't even see.
It's totally distracted. And that leads to instability, noisy outputs, and just glacially slow training. I mean, to put a number on it, a previous model, PixelFlow, was taking about 1.6 seconds per iteration. DeCo gets that down to 0.24 seconds.
That's a massive difference.
Yeah.
The efficiency gain alone is enough to make you pay attention.
Yeah.
So let's really unpack how DeCo does this, the separation of the DIT and the pixel decoder.
Okay, so structurally, it's a really clever division of labor. First, you've got the workhorse, the diffusion transformer. But its job has been made much, much simpler. It never even sees the full resolution noisy image.
So what does it see?
It only operates on a downsampled low resolution version of it. They call it XBART in the paper.
So that's the first big strategic move. By just showing it a blurry version, you're physically filtering out all that high frequency detail it was getting stuck on.
Exactly. And they double down on that by using a really large patch size, like 16, which is way bigger than what older models used. That forces the DIT to look at the big picture, to learn the overall structure, Its only output, which they call C, is just the semantic condition. It's the plan.
So the DIT is kind of like the art director. It figures out the composition, the shapes, the general idea. But then you need someone to actually paint the details.
And that's where the lightweight pixel decoder comes in. This little module does get the full resolution noisy image as input, but it uses a tiny patch size, like 1. And the key thing here is that this decoder is built for speed.
It's attention-free, right?
Totally attention-free. It's just a few linear decoder blocks, maybe 3 layers deep. It's tiny, only about 8.5 million parameters. It's fast, and it's designed to just manipulate pixel data without the massive overhead of self-attention.
Okay, so that split makes perfect sense. A big model for the hard semantic problem, a tiny, fast model for the simpler detail problem. But how do you get them to talk to each other? How does the art director's plan get to the painter?
That's the other critical piece of the puzzle. It's a mechanism called adaptive layer normalization, or ADAL-N. So the semantic condition C that comes out of the DIT gets upsampled. Then a small network uses that condition to generate these modulation parameters: alpha, beta, gamma.
Okay, so we don't need to get lost in the Greek letters, but the idea is that the DIT isn't just sending information, it's sending control signals.
That's the perfect way to put it. It's generating signals that tell the decoder how to behave, how to apply the fine details. It's not just, adding its features on top like you might see in a UNet. It's dynamically controlling the internals of the high-frequency network.
Which is much more precise.
Way more precise. And their ablation studies showed this. Just adding or concatenating features was way less effective. This ADAL-N on modulation lets the DIT's low-frequency knowledge guide the process without the DIT ever having to touch the high-frequency noise itself.
And they actually proved this was working, right? They did an analysis using a discrete cosine transform.
They did.
Yeah.
The DCT energy spectra was the smoking gun. When they looked at the output of the DIT inside DeCo, the high-frequency energy was massively suppressed compared to a baseline DIT.
Proof that it learned to ignore it.
It successfully handed off the job. But then, crucially, when they looked at the final output, the predicted pixel velocity, it had high energy across all the frequencies. That proves the little pixel decoder successfully picked up the slack and painted in all the necessary detail.
The architecture just works. It forces each part to specialize. Okay, let's switch gears from the architecture to the loss function, because this part is also really fascinating. They use human perception to change how it learns.
Yeah, the frequency-aware flow-matching loss. This is where they get really clever.
So a standard loss function, like L2, it treats every single error the same.
Right. An error in a pixel that's part of some random noise you'd never even notice is penalized just as much as an error on the edge of a person's face, which is, kind of silly from a perceptual standpoint.
So DeCo tries to be smarter about it. It prioritizes what we can actually see.
It does. And to do that, they basically borrowed from the science of image compression, specifically JPEG. They take the predicted and the real pixel velocities, and they transform them into the frequency domain using DCT on little 8x8 blocks.
And they convert to YCBCR space first, which is important because that separates brightness from color.
Super important, because the human eye perceives those differently. And once they're in that frequency domain, they apply these adaptive weights, and the weights come directly from JPEG quantization tables.
Okay, so unpack that. How does that work?
Well, the whole idea behind JPEG is that our eyes are really sensitive to changes in brightness and low-frequency stuff, but we're not very good at seeing high-frequency changes or shifts in color. So JPEG just throws a lot of that information away.
Right, it quantizes it heavily.
Exactly. So DeCo looks at those quantization tables. If a certain frequency is something JPEG would normally discard, meaning its quantization value is high beam, DeCo gives that frequency a very low weight in the loss function. It's literally telling the model, hey, don't waste your energy trying to get this bit of high-frequency noise perfect. Nobody's going to notice.
That's brilliant. It's like building a perceptual shortcut right into the training objective.
And it's not just a cute trick. It really works. Their ablations showed that using a JPEG quality factor of 85 gave the best results, an FID of 31.35. If they turned it off, used a quality of 100, which is lossless, the FID got worse. It went up to 33.84.
Wow. So explicitly telling it to ignore unimportant details actually makes the final image better.
It simplifies the problem for the model and lets it focus on what matters.
All right, let's talk about the final numbers. For the people out there who really follow the state of the art, the benchmarks have to be convincing. How does DeCo really stack up in quality and, maybe more importantly, speed?
In terms of pure quality, it's a leader among the end-to-end pixel models. On ImageNet, it hit an FID of 1.62 at 256 by 256 and 2.22 at 5 through by 512. That's a huge deal because it means pure pixel diffusion is finally truly competitive with the best VAE-based latent models. They've closed that quality gap.
That's impressive. But the efficiency is the metric that really blew my mind. A model being 10x faster to train, that changes everything.
It absolutely does. When we say 10x faster, think about it like this. DeCo got to an FID of 2.57 in just 400,000 training iterations. That's about 80 epochs.
And the baseline.
The baseline model needed 800 epochs to get to a similar performance. For any lab or company, that's the difference between running an experiment for a week versus a few months. It's millions of GPU hours saved.
It redefines the economics of doing this kind of research. What about on the other end? Inference speed for actual applications.
It's fast there, too. It can generate a high-quality image in about a second using 100 Euler steps. Compare that to older cascade methods that took almost 40 seconds, or even other single-stage models like PixelFlow that needed almost 10 seconds. It's just a much more efficient architecture all around.
So there was other work happening at the same time, right? Like GT. They also saw this high-frequency noise problem, but they came at it from a different angle.
They did, and it's a really useful comparison. GT tried to solve the problem by changing what the transformer predicts. Instead of predicting the high-dimensional noise, they had it predict the clean image, which is a lower dimensional target.
A logical approach.
It is, but DeCo's architectural solution, actually separating the tasks, proved to be more effective. In their head-to-head tests, DeCo got an FID of 31.35, while GT only managed 39.06. It confirms that specializing the modules works better than just changing the target of a single monolithic model.
And this wasn't just for class conditional stuff. They took this into the big leagues. Text to image.
And it translated very well. They trained it on the BLIP30 dataset with a Quinn text encoder, and it achieved a leading score of 0.86 on the GenEval benchmark. That puts it ahead of some huge names like SD3 and FLUX.1 Dev, and it handles multiple languages too, Chinese, Japanese, English. The core architecture is just fundamentally solid.
So when we zoom out, what's the big picture here? It feels like DeCo has really broken through that core trade-off that was holding pixel diffusion back. You don't need a VAE to get top results, and you don't need to wait forever to train it.
I think the main takeaway is just the power of specialization, guided by domain knowledge about signal frequencies. They built a system where the DIT isn't fighting a hopeless battle against high-dimensional static anymore. It's laser-focused on learning semantics.
And they offloaded the detail work to a specialist.
Exactly. They offloaded it to a simple, fast, attention-free decoder. So you kind of get the best of both worlds.
Yeah.
The robust semantic learning you'd want from a latent model, but with the perfect artifact-free output of direct pixel modeling.
That structural design, especially using ADL-N to have the DIT control the decoder, it raises a really provocative question for the future.
What's that?
Well, if the DIT is now just a pure semantic backbone acting almost like a text encoder, but for visual structure, could this decoupled design become like a universal blueprint for generative models?
You mean a single semantic core that you can just plug different decoders into?
Exactly. You could have one core architecture, and if you want to generate at a different resolution or even a different modality, you just swap in a different specialized lightweight decoder. The idea of a universal semantic engine, that's a really powerful thought for where this field could go next.